So if I go to my Z table, and I look up negative 2 point, what was that? Negative 2 point what?
157.
157, so negative 2.1. And on my Z table, I have to look up I can't look it up to 3 decimal places, I can only look it up to 2 decimal places. So negative 2.1, and if it was 57, I'd round it to 216, right? So I'd go over here, and I get a p-value of 0.154. Does anybody remember what I just said that was?
No, mine's different.
Yeah. Where am
Negative 2.16, so negative 2.16, I get a p-value of 0.154.
Yeah, mine is 0041. If H is false, then there's a chance
That's the p-value associated with the calculated test statistic.
But none
Okay.
of that has to do with the alpha yet.
Huh?
None of that has to do with the alpha.
I haven't done anything with alpha yet. Okay? So now what I'm going to do is I'm going to look at this. I'm going to add 2 lines. Okay. I can use Excel to get that. If I don't want to use the table, my aspect is I tend to use both the table and Excel because I never trust myself. The Z table is called what table?
Normal.
Normal. So I'm going to start typing in. So I hit equal and I'm going to start typing in normal. Now you see I get a whole list of things. Most of the time I'm going to be using norm S distribution or norm S inverse. The distribution gives me the values from the meat of the table. The inverse gives me this number. No, it gives me the test, it gives me a table number related to some specific alpha. Okay? But I don't know the specific alpha, so I want the normal S distribution. And the 2 things that I'm going to put in is the Z-score. Well, we just calculated the Z-score. And then you normally have to put in a thing where it says whether it's cumulative or not cumulative. And here's why I use both the table and Excel. I get this flip-flop. I'm either going to type in true or false here. One of them gives me everything to the left, and one of them gives me an exact value. I'm like 70% sure that I want to type in the word false. And when I did that, I got 0.038, which is not what I got down here when I looked it up. So see, I was 70% and I was wrong.
Still.
So I don't want false, I want
True.
true.
If you find
away.
the p-value.
Go away. I know what I did and I can't fix it without you going away.
Oh, I got it right.
I'm glad you got it right because I made a typo here and it won't let me fix it.
So that's the p-value, and if I want the q-value, I just go minus, one
No,
minus that?
that
has
this
nothing
is
to
a
do with
different
this.
P.
Oh, that's where I'm getting so lost. Gosh, there's too many different.
I know, but it won't let me with the dialog box up.
Should I hit OK and then back?
I tried to do that and it,
Oh, now it wants
Oh,
to
that's
work.
on top. There.
okay. So norm, so I want to click on this, comma, and true.
Uh-huh. Yep.
And that gave me the same p-value that we looked up in the table.
Close.
See, when you ask, remember I keep saying I can't memorize everything?
Oh, yeah.
See, so this is why I use both the tables and the electronics. Because I can't remember which word, but it's true. So that gives me a p-value. Now, I can also get this thing that's called a table value. Now, here's what I was looking at in this problem, and one thing that we got to learn in this book is this book, if I'm looking at this assignment, does this book anywhere, so we said that the p-value was what? 0.015? And it says 4 decimal places, 1.4.
The t-value, that would be the t-table?
That's the p-value from the table when I looked up the test statistic, the probability. Now what this is saying is the probability that I would get a mean that was that much lower than the 50,000 is about 0.15%. That calculated test statistic is so far away, I would only expect that to happen about 1.5% of the time. That's what the 0.1, that's what the p-value is telling me.
Okay, the probability that the 50,000.
No, the probability that I would get a mean of 46,900 would, if the actual mean was 50,000, if the 50,000 was real, I would only expect to get a mean of 46,900 on a sample of 31, about 1.5 times out of 100. So what this is saying is that's an unusual number. I would not expect that to happen. Now, what we tend to do is we look at this and we compare the p-values, or there are two things that I can compare. I can compare the p-value to the alpha. And I can use that to make a decision. Or I can compare the test statistic to a table value. So here's where these sort two comes in. This is what we got when we calculated the test statistic. Now, I have to choose an alpha. If they don't give us an alpha, the book says default. Does everybody know what default means?
Yeah.
That means if nothing else is given, this is what we're going to use. So the default alpha, if alpha is not given, is 0.05. 0.05 is always my default alpha if alpha is not given. If alpha is not given, that's the alpha that I'm going to use. So now what I'm going to do is I want to get a table value for this alpha. So what I'm going to do is I'm going to look up the alpha for 0.05. Especially considering this is a right-tailed alpha. Since this is an alpha over here, so that means whatever the z value is. So if I go back to my table, my z table, and I look up 0.05, we get 1.645. When we look up 0.5, and remember we were doing this when we were making confidence intervals, right? So I'm still going to go back and look at that. So I want an alpha of 0.05, so I get 1.645. And to be perfectly honest with you, we use that so often in the z table, I tend to memorize that. So we know that z for that is a negative 1.645. If this is a lower tail test, if this was an upper tail test, I would still use this value, but I would use the positive. So now I'm going to look at this, and here my table value is negative 1.645. This is the z from the table for a 0.05 alpha. Now here's where I make my decision. I can either compare this number to this number. I can compare these two numbers. If this number is out in the tail, that means in this particular case, it's less than this. That means I reject the null hypothesis. So if I look at this, and here's where I'm going to look at this, is if I'm doing a lower test, if the calculated test statistic and I'm going to be a little bit lazy because I don't care whether I'm using the upper side or the lower side. I'm going to just look at the absolute value of that. I'm just going to compare the absolute value of the calculated test statistic. So in this case, I got the negative 2.1. I'm just going to compare 2.1. And I'm going to compare it to the absolute value from the table for whatever my alpha is. So remember we just went and looked that up? If the calculated test statistic is greater than the table value, so if the calculated test statistic is greater than the table value, we reject the null hypothesis. The null hypothesis was what?
Greater than 50,000?
Greater than or equal to, because the null hypothesis has always got to have a equal sign in it, right? So what I'm going to say is, if I'm looking at this, see if I can, okay. there is statistically significant data to reject the null hypothesis that the mean of the mileage of the tires is greater than or equal to $50,000, 50,000 miles. There is statistically significant data to reject the null hypothesis that it's actually equal to. So we are going to accept that the alternative hypothesis, that it's less than 50,000 miles, is true. So we see a tire company made a claim, their tires get 50,000 miles. We went out and took a sample of 31 tires. They had an average lifespan of 46,900 miles. We went and did some calculations. We made a test statistic, and we were able to decide whether or not we would accept or reject the null hypothesis.
What is that TL at the very end?
We believe there is statistically significant evidence.
Or is that an H? I maybe it didn't. Oh,
Therefore. Therefore, we accept the alternative hypothesis. Those are the steps we go through every time. Yes, it is a lot of work. You notice I let Excel do a lot of the calculations for me. Now, this was one way I could decide whether to reject the null hypothesis or not. Another way to do this same decision is, remember, I went to the table, I took my calculated test statistic and went to the table and looked up the probability, right? That's what the p-value is, the probability that that test statistic would actually come up.
The calculated test statistic and the table value. Okay, so if the calculated test statistic, which was the 0041 for me, or no, test statistic was negative 2.644 for me.
Correct.
And then the table value was the negative 1.645.
Correct.
Which made it more.
Correct.
Then we reject the null hypothesis.
Correct. Now, I can look at the p-value for the calculated test statistic. And that will always be a positive number. It can never be negative, because it's a probabilities. Probabilities have to be between what?
1 and 0.
1 and 0. So it's got to be a positive number. So I can also look at the p-value for the calculated test statistic.
Isn't negative 2.64 less than negative 1.64?
The negative part, yes, but remember what did I say I'm actually comparing?
Calculated.
The absolute value, because I don't care if I compare the absolute values, it doesn't matter whether I'm doing a lower tail test or an upper tail test, it will still come out to be the same aspect. I don't have to take sign into consideration.
Okay.
So I compare the absolute values, not the actual numbers.
No.
Where does this table come from? Where does the table value come from? It comes from the known
Alpha.
alpha. So I can actually compare the p-value to alpha. And this one is just the opposite. If the p-value is less than alpha, I make the same decision. So if the absolute value of the calculated test statistic is greater than the absolute value of the table value, I reject the null hypothesis, or if I look at the p-values. And the reason we gotta look at both of those is sometimes if you just dump data into a computer program, they don't give you the table values, they give you the p-values. So you gotta get comfortable doing both. I personally normally look at the calculated test statistic and the table value. To me, they're easier to compare. Actually, when we do the t-test, they're actually easier to get. It's actually harder to get a p-value for the t-table. The p-value for a z-table is easy to get. We just were able to look it up. The p-value for the t-table is a little bit harder.
This doesn't have anything to do with measurement. It's just
What
like
do you mean?
I guess I'm not understanding the actual measurement that goes on with this. There's not a
What do we measured the life of the tires, how many miles you got on each tire.
Okay, so that 1.645 would be like per mile?
That is that is the value that when we look at the probabilities, that is the value.
So it doesn't ever calculate like what I'd get per mile?
No.
Not in any of these statistics?
No.
That's what I meant.
Yeah, it's not
Okay.
calculating this. What the negative 1.645 represents is the 1.64 standard deviations below the mean. See, what this is saying is that this 46,900 is 2.157 standard deviations below the mean. So when we calculate that, what we're saying is that number that we got is more than 2 standard deviations below the mean. Remember when we were talking about standard deviations from the mean?
Mm-hmm.
We're just so far away from the mean that we're more than 2 standard deviations away from the mean. So what this is saying is here, if I'm more than 1.645, that means I have 95% of my table is up here. So I would expect 95% of the time if I was doing this, I would get something that is a calculated test statistic that's up here. That would be less than the table value. If this was actually if the 50,000 miles was actually true, I would get that 95% of the time. 95% of the time when I did the calculation, I would get something that was greater than 1.645. It would be somewhere up in here. So this is a rare occasion. It happened way out here in the tail. It only happens 1.5% of the time. I would only expect to get a mean that low 1% of the time, a little more than 1% of the time, if what they were saying is true. If the null hypothesis was true, I would only expect to get a mean that small 1.5% of the time. So it's just saying that that this would be a rare occasion. But see, that's the type 1 error. On the rare occasion that the null hypothesis was actually true, that the tires actually do get 50,000 miles, I would this would be the rare sample or the rare occasion that I came up with that.
Okay, so my p-value says 0.0041. So it's saying that only like
0011,
0041?
0041, is it? 0.041,
0041.
0.00, that means it's happening less than 1% of the time. That's even more rare.
So that the chances of it being more than 50,000 is like only 1% of the time.
Being 50,000 or more.
Oh.
Because, yeah. So yeah, you got a much smaller one. So now let's go back and I'm going to look at problem number, let me see. Let's look at problem number 26. So in problem 26, oh man, I thought that was, is that 26 or 25? That's 25, this is 26, okay. Does somebody want to read that for us?
Registered nurses earn an average annual salary of $69,110. For the same year, a survey was conducted of 41 California registered nurses to determine if the annual salary was higher than $69,110 for California nurses. The sample average was $71,121, with a sample standard deviation of $7,489. Conduct the hypothesis test at the 5% level.
Okay. So what, am I testing means or proportions? Means.
Means.
Because I was talking about the average annual salary. Okay, fantastic. Is the standard deviation of the population known or unknown?
No.
We have a sample standard deviation.
We have a sample standard deviation. We do not have a population standard deviation, which is going to be the case most of the time. Most of the time, we're not going to have that standard deviation of the population. What we just did was a rarity, but it happens from time to time. Okay? So, what's my null hypothesis? Well, first off, is this a directional test or a non-directional test?
Directional.
Directional. Why do we say directional?
Because either less than or greater.
Be more specific.
As they get paid higher than 69,000.
There you go. The question here is, the salary is higher than $69,110 for California nurses.
A lot of money.
Okay? So my null hypothesis would be less than, your null hypothesis, and since they don't have an equality statement, I'm going to have to go with this one. They got greater than or equal to, wait. Yeah, the null hypothesis has always got my equality in it, right? And they want to know if the salary in California is greater than. So since they don't have less than or equal to, I'm going to go with the equal to.
And then the alternative will be a greater than.
Then the alternative will be greater than. $69,110. In all honesty, it's easier sometimes to come up with the alternative hypothesis first and then go back and write the null hypothesis.
Oh yeah, I see.
Okay. So, what does my X bar represent?
The mean of the population.
No.
The X bar is not the sample mean?
It is the sample mean. So what is the sample mean of?
74.
The 41 registered nurses in the sample?
71,000.
71.
Oh, yeah.
71,000.
121.
What does that represent?
The salary?
Yeah, what does it represent? It represents
The
the
average
Average.
salary.
average annual salary. It's not a number, it is a thing. Okay. What distribution am I gonna use?
The normal?
No.
No?
We use the normal distribution when
Oh.
what?
Only if we have the standard
If
deviation
the
of the
standard
population.
deviation of the population is known, since the standard deviation of the population is unknown, I am going to use the
T-table.
T-table. And when I use the T-table, I need to use what?
Degree of freedom.
Degrees of freedom. Now to get to the degrees of freedom, I need to enter a subscript. On the Apple, I think it's easier. I think it's the shift,
The shift underscore.
shift underscore. On PCs, it's a little bit different. I have to go and look at it. I can't remember. Whoops. On the PC, it's control equal. So on the Apple, it's shift underscore. On the PC, it's control equal. So when I'm doing this, I got to come over here, and since I'm on a PC, I hit control equal. Whoops.
That's, yeah, it's not working.
Yeah.